Good morning, students. So now I'm going to explain you in one of the lab experiments, RC phase shift oscillator. So what we require, the aim of the experiment is that design and set up RC phase shift oscillator using BJT and calculate the frequency of the output waveform. And when you design it, you will be designing it for a certain frequency and calculate the output waveform frequency and just verify the frequencies that has been produced. So this is the circuit diagram. As you all know, for the oscillator, you require an amplifier and a feedback circuit. And here you can see this part is an amplifier circuit where you have R1, R2, RC and RE. This is your amplifier circuit, right? And the output of this amplifier, you see the output from the collector N has been taken and is fed back as an input to the amplifier. So the output it gets divided into three stages of CR, CR and CR. There are three CR networks and the output gets divided across these three divisions CR and one CR second and the third, and the portion of the output reaches as an input to the an amplifier circuit. So you have only the biasing voltage plus 12 volts is applied to the VCC and no other inputs are inputs like we have AFO is not provided here. The oscillator produces its own waveforms and here it is a sinusoidal waveform it produces and the frequencies used for an RC phase shift which it produces are lower frequencies, that is we call it as a that is range from 2 to 1 kilohertz to 5 or up to 10 kilohertz. We can recommend RC phase shift oscillator lower frequency ranges, or usually say audio frequency ranges are generated usually 1 kilohertz, 2 kilohertz, 3 kilohertz lower ranges of frequency. If you want to generate, you can prefer RC phase shift network. Here for an oscillator, two conditions has to be satisfied. That is the magnitude of A beta, that is magnitude of A beta should be greater than or equal to 1 and the total phase shift should be equal to 360 degrees or 0 degrees. So here you can see the transistor, how much amount of phase shift is produced by the transistor. Yes, that is 180 degrees of phase shift is produced by the transistor when you are inputting at the base and taking an output across the collector. So 180 degrees is produced here and the remaining 180 degrees I have to produce from the feedback network. So here the values of C and R are taken such that it produces a 60 degrees of phase shift. So each you have three stages of CR network. So in each of the stage produces 60 degrees of phase shift. So total 180 degrees of phase shift that is developed by the feedback network. So total you have 180 plus 180, that is 360 degrees of phase shift is produced, that is equivalent to 0 degrees. So phase shift criteria is satisfied and also A beta should be greater than or equals to 1. That is also satisfied while designing. So the design of only the frequency you have to do and the design of the transistor is not mentioned according to the syllabus, but then also you can just have the voltage divider, you know the biasing, voltage divider biasing, this is an voltage divider biasing. We make use of the voltage divider biasing so that you get a stable output for a transistor and that is Q point is stable. So you can design the transistor using the method of voltage divider method biasing. So you can design this. You can see RE is 220 ohms, which is less than the RC, and R1 and R2 you can see 15 kilo and 2.2 kilo ohms. You can have design. And this is your feedback circuit, this is your amplifier circuit, this is the RC phase shift network. So next is design. Only the design part of the RC network we are dealing with. So the frequency equation is given by 1 by 2 pi RC square root of 2n. Don't bother about the derivation. So you have to make use of this equation. And here we have three stages. So because we want in 60 degrees of phase shift, so we have three stages, each stage producing 60 degrees of phase shift. So n indicates the number of phases. So 2 into 3 gives you root 6. So equation is 1 by 2 pi RC into root 6. This is the exact expression. Otherwise, generally we can make use of generalized expression is F equals 1 by 2 pi RC. So we'll use the exact expression because we are doing it practically and we want to verify that. So F equals 1 by 2 pi RC into root 6. You can see you have one equation, and in designing you have to design this RC components itself, tell you what is the frequency that is generated by RC phase shift oscillator. So you have two unknowns. F will be given to you. You have to design either for 1 kilohertz, 2 kilohertz, whatever is given. So here example is taken for 1 kilohertz. And so you have three stages. We will assume that each has to produce 60 degrees phase shift. So we'll have to assume that C1, C2, C3 are equal, and we'll designate it as C, and R1, R2, R3 are equal, and it will let it be equal to R. So when you have the equation, one equation and two unknowns, most of the best method is to always assume C value and calculate the value of R. If I assume C equals to 0.01 microfarad, just substitute C value as 0.01 microfarad, and all other values you know the F value. Only the term which you don't know is R. So calculate R using R equals to 1 by 2 pi FC into root 6. So when you calculate that, you will be getting R equals to 6.49 kilo ohms, and the standard, you won't be getting 6.49 kilo ohms. So you have to use the standard value. The standard value nearer to this is 6.8 kilo ohms. So this is about the your RC phase shift oscillator. So let us design using a multisim. So you have multisim, using multisim you have to design this RC phase shift oscillator. So you have to take all the components, first place all the components. So select, so what you require capacitor of 0.47, the capacitor, right? So I'm taking first I'll place all the components that are required, and the capacitors of 0.01 I require, right? 0.01 microfarad. So you can type it, or if you just select this capacitor, you get all the values. I'm written 0.01 microfarad. So this I want three numbers. So you can even copy and paste it. Just selecting it. So you require resistors, right? So resistors 6.8. It was in the design we had used the 0.01 microfarad. So what are the value we had got near to, that is 6.8 kilo ohm we had got. So we will make use of that 6.8 kilo ohm. Okay, three numbers I require. It should be 6.8 kilo. This 6.8 kilo, 6.8 kilo. What else I require? I require a capacitors are wrote, one more capacitor, that is 0.47 microfarad. So we have seen here what was the reason. We had 47 microfarad also. So 47 microfarad capacitor that I have to 47 microfarad. Okay. So first I'll do next I'll take this transistor BC109 is there, that's what I wanted, so I'll take that. And you required what, that is 15 kilo ohm resistor, the back for the transistor, whatever you require, that is basic resistor. In resistor I required what, 18 kilo ohm. I required 18 kilo ohm, so 18 kilo ohm resistor. And, okay. And what else I had required? I had required 2.2 kilo, 2.2 kilo, and I wanted 220 ohm, 220 ohm, and one more I required was 1 kilo ohm. I will just type this 1 kilo. You can find 1 kilo. Okay. So probably, and the supply, one supply, that is sources. So plus VCC I require. I put this here. So let me remove the 6.8 ohm. I want to put 6.8 kilo ohm. So that I have taken the 6.8 ohm. Um, okay, 6.8 kilo ohm. Okay. And one more resistor of 6.8 kilo ohm I wanted. So I'll copy. You can even do like this. Copy and paste here. So you will get one more 6.8 kilo ohm. So I'll place all the values at the required place. Okay. So let me place this and 6.8 kilo ohm. Such at the base of the transistor what I require 18 kilo ohm. So I'll rotate them first, rotate 90 degrees. This and get it here, and this I'll place here. And this also I require here. Next is what else I require. Below this is R1, R2 was 2.2 kilo ohm. So where do you find this 2.2 kilo ohm? Make this as 2.2 kilo ohm, 2.2, this 2.2. Rotate this. Okay. So this is R1 and R2, and RC was 1K. This one, rotate it 90 degrees. RC was 1K. Replacing this same line. And RE was 220 ohm. Rotate this. Place it here. Okay. And 220 ohm. Next, I wanted 0.47. So here it was 0.47. And 0.01 I require down for the feedback. Okay. Next, I wanted 0.47 at the base. Okay. Next, 5 volts I wanted here. Right? At the top. And then we'll do this. What we have to do is we just remove it here. And we select this. You get it. Then select hole. Now you select hole and place it here. Okay. You can change this value to, I wanted around 12 volts. So I'll put it as 12. Even 10 volts is also sufficient. I'm getting 12 volts. Next point, place this 6.8 kilo. I'll rotate them and place it here. And we'll rotate this 6.8 kilo and place here. And rotate this 6.8 kilo place it here. Okay. In between these resistors, I'll place the capacitors and one more capacitor here, and this register. Okay. Now this 0.47 I require here, just rotate them 90 degrees, right? So now just go on making the connection. So what are the connections? From R1 and R2 I connect, and from base I connect to this junction, and then to the RC, and from this to this place in here, and one from here, and this what you can do is just mention the junction, so you can have more than two connections. So now this is junction you can have. Next, this is also junction. Okay. This is junction there again. This connection is yours. Okay. And we are taking output from this point. And there is some connection. Okay. And we can connect this here, and this to the all capacitors I connect here, and between these two also I connect. Okay. And this one to this junction. So this is the connection. And what else you have to do? You have to connect these resistors. Okay. And now connect them here. And connect them here. You have to take the junction again. And mention the junction. Place a junction. It is a point where you can have more this. And take the junction. Place it here. Okay. Connections are over. And one more we have to place is the ground. So I have taken the ground. So one more ground I require. Okay. So one ground at the amplifier. And I need a junction to be present here. Then only you can have more than two connections. Okay. So I have done this. This is ready. I'm ready with the circuit. Just add a to measure to note down the output. You need a oscilloscope. Place this oscilloscope here, and you can observe the output at this point. Okay. And the circuit is ready. Now we can simulate it. So, finally, I place the support, the circuit diagram 220 ohms, 2.2, 16K, 1K, this is 16K. So now the circuit is ready. So you can run the circuit, you can simulate it. So I'm simulating the circuit. Double click the oscilloscope. You are getting see you are getting a sine wave oscillator output. And just I stop this to measure the frequency. So I have stopped the simulation. So you have two bars here. You can just separate them. Place it here on the tip of that is peak, one peak. I want to measure what is the cycle. So I place it here at the highest value. So second, this point I'll place here. Okay. This tip and this tip gives you T2 minus 1. This is your T2 and this is your T1. T2 minus T1 has 757.576 microseconds, and you can check it as 1 divided by 757.576 microseconds. That gives you roughly around, what I tell you, that is 1 divided by 757.576. So it gives you 1.3 kilohertz. So you have designed for 1 kilohertz, but usually the difference in small amount of resistors that will be counted, and here you are getting it at 1.3 kilohertz. Okay, so this is how you have to check. So these are the peaks. You can even keep these peaks at the other ends also, that is at the 0 point of this, and next you can place here where the 0 starts. Okay, so same 738.625 in 636. Small amount of difference you can find if you are not placing it correctly. You can even expand this, like if I can expand it to 500, you can see they are almost exactly placed. You can check this minus 272 millivolt and 147 millivolt. So nearer to 0 they are. So you are getting here the difference. 369.318 when the box is at here I have to place, because this is the negative going edge. So next negative going edge I have to place here, or positive going edge to positive going edge. You can see, so in the same range I am getting the values. Okay, 730. So this is the output of your RC phase shift oscillator sine wave, and your verified frequency T2 minus T1. So this is your RC phase shift oscillator. Okay, thank you.